Yeah. Afternoon, everyone. And afternoon to those who are joining us from online. Thanks a lot for making time to join us on this special lecture. For those who are not familiar with the organization that is actually leading this distinguished lecture, it is called the International Association of Mathematical Geosciences. So typically on an annual basis, or biannual basis, they elect people who are distinguished people in a particular discipline to go around the world giving some sort of different lectures that aim to ensure that knowledge is shared with each and every one, especially in mathematical geosciences. So today we have the honor and the pleasure of hosting Professor Renguang Zuo, who has actually received his BSc and a PhD degree from the University of China, Geosciences or CUG in Wuhan in China, in 2004 and 2009, respectively. He is a current full professor at the State Key Laboratory of the Geological Processing and Mineral Resources in China. And in 2014, he was a senior visiting fellow at the James Cook University in Australia. His research focuses on big data analytics, machine learning, based mineral prospectivity mapping, and geochemical anomalies identification. Prof. Zuo has published over 200 peer-reviewed papers and about 6 books and many book chapters. He served as a guest editor for 8 special issues in the International High Quality Journals. His publication has actually received over 11,000 citations based on Google Scholar across a range of esteemed international journals. In 2023, Prof. Zuo was awarded the Gold Medal, which is the highest award by the Association of Applied Geochemists, or AAG. In addition, he was the inaugural recipient of the Karaka Award by the International Association of Geochemistry in 2015. Meanwhile, he was also recognized as the Elsevier highest cited Chinese scholar and the world's top 2% scientist. So Prof. Zuo is the current president of the Association of Applied Geochemistry, which is going to be holding this title for 2026 and 2027. And he was the council member of the International Association of Mathematical Geosciences between 2020 and 2024. He has received fellowships from AAG, the Society of Economic Geologists, and the Geological Society of London. He has been heavily involved in the editorial boards of many science index journals, including the Journal of Chemistry or Journal of Geochemical Exploration, Journal of Geochemistry, looking at exploration, environments, and applied geochemistry. He has also been involved with the Natural Resources Research and all geology reviews, and applied geochemistry and the Journal of Earth Sciences. So there's many journals that he's been working with. Lastly, I would also want to say that if you are interested in mathematical geosciences, it's quite easy for you to become a member. Just go to the website and you can read the instructions on how to become a member of the International Association of Mathematical Geosciences. We'll also have a conference this year in Canada, which you can attend later on in the year. Anyone who's working in this particular discipline or more interested. So I hope you're all going to be enjoying today's lecture, and feel free to engage. We have over 30 minutes allocated for discussions on any questions that you may have. So, Prof. Zuo, please welcome.
Hello, everybody. Thanks so much for this introduction and for your invitation. I'm Renguang Zuo, coming from the China University of Geosciences, Wuhan. And I'm lucky for the distinguished lecturer for the International Association for Mathematical Science. And the last 3 days, I gave a lecture in the University of Free Space. So I'm very happy to visit this work and give a talk about the data technology visual-driven linear perspective. And this is the outline I thought I will first discuss what's the big data and big data analytics. What we know, the big data has the 5 waves, the characteristics, including the volume and the velocities, variety, and the values. And for some data, it has nice size, rapid changes, diverse sources, and inherent uncertainty. Therefore, some data are special big data. And this table shows the difference between the traditional analytics and the big data analytics first, and the traditional analytics mainly focus on the descriptive and diagnosis analysis, but big data analytics mainly focus on the predictive analytics reported by data science and let data speak themselves. The second, the traditional data analysis usually use the limited, clean with simple models, but the data analytics usually use the raw data like scale and more type of data, especially support by the complex data models such as deep learning. I will talk about later. And finally, I think was this the most important, the traditionalities maybe support the positions, and sometimes your scientists will ask what happened and why. But big data analytics usually focus on the correlations, and they can be lead you insights and more correct answers. Then I will simply introduce artificial intelligence, deep learning, and machine learning. The concept of AI was proposed in the Dartmouth conference, and in 1966, and this year was considered as the start point of the AI. And what's an AI? AI is defined as the technology science decided to investigate and develop several methods, technologies, and application systems that enable the simulation, improvements, and intentions of complex human intelligence. You could say AI is very big group. For example, AI including the planning, scheduling, algorithm, and machine learning. And machine learning is a subset of AI. And machine learning also contains many methods. For example, supervised learning, unsupervised learning, and deep learning. And this shows the ratio among AI, machine learning, and deep learning. Machine learning is subset of AI, and deep learning is a type of machine learning with more complex architectures. In 1950s, early AI first experiments. In 1980s, machine learning began to flourish, and in 2020s, deep learning breakthrough drive AI boom. And this shows the paradigm shift of AI from for system machine learning, deep learning, and nowadays the general intelligence. They are different from the input data, examples, groups, and correlations. And from export system to and from the export system to machine learning, we have addressed the knowledge in general. And from the machine learning to deep learning, we have addressed the feature in general. And from the deep learning to nowadays general intelligence, we have addressed the customized. And this shows the machine learning consists of supervised, unsupervised, semi-supervised, and reinforcement learning based on the training samples. If the training sample, we can use the supervised learning. If the low training sample, we can call this the unsupervised learning. If we use the positive and negative training sample, can be used the semi-supervised, and another is the reinforcement learning. As we know, machine learning consists of three layers. One is the input layer, and hidden layers, and output layer. Machine learning could be classified into shallow machine learning and deep learning. Based on the number of the hidden layers, if one machine learning has only one hidden layer, hidden team will be called it as the shallow machine learning, such as the artificial neural network and support a worker machine. But if the number of hidden layers is much more than two, we can call it the deep learning, such as the convolutional neural network and deep leaf network. And this figure again shows the difference between shallow machine learning and deep learning.
ఇది AI గురించి చదువుతున్నాడు అది యాక్చువల్గా, కానీ సౌండ్ రావట్లేదు వాడిది. कौन बोल रहा है? चीना.
Thank you. Okay. And machine learning some requires manual feature extraction and then classification or prediction, but deep learning can automatic for the feature extraction and then classification and prediction. This executes the therefore deep learning can the raw data, but shallow machine learning sometimes we require to feature extraction and then classification and predictions. And there are two paradigms in geoscience discovery: logic-driven and proof-driven. This compares the traditional logic-driven with data-driven analysis. Logic-driven would methods rely on theories and expert logics and rules. Data-driven methods extract patterns and insert directly from the data. They use machine learning to find hidden correlations in large datasets. So there are two different paradigm. Next, we will focus on the linear prospective (MPM). What's the linear prospective deals the probability of chance that linear deposits of a third class can be discovered in the area, because the geology of the area is conducive or favorable to the formation of such class of mineral deposits with similar to the mineral probability or mineral potential. Next, I will highlight some important work in the field of MPM. In 1989, Professor Fritz introduced the width of offsets for MPM. This study is published on Science, maybe the first publication in Science. Width of offsets is the most popular method for MPM because it is intuitive as well as easy to carry out and interpret. In 1992, my PhD supervisor, Professor Zhao Tongda, who is the father of mathematical science in China, discussed the basic theory, principles, and methods for the statistic prediction of mineral deposits. In the same year, Professor Wang Shiteng, who is a master supervisor of Professor Cheng Qiuming, proposed the comprehensive information methods for MPM. In 1993, Professor Dang Zehner proposed the three-part method for mineral resource assessment. In next year, Professor Bohem Carter discussed the data-driven and logic-driven methods within GIS. And in 1990, my PhD supervisor, Professor Chen, and his team proposed the Central Asian area, spatial area, and local singularity analysis, which has become big tools for spatial data analysis. And in 1999, Professor Chen and Professor Atwood proposed a fuzzy width of evidence based on the fuzzy sets and the fuzzy probability for MPM. In 2008, Professor Chen further proposed nonlinear survey and Poirot models for mineral resource assessment. And in 2000, Han and Harris introduced West method for for geo information retrieved from the web specific sites. In 2008, Professor John Kwanzaa published the book and developed GIS-based NPM and geochem-alumni identification. Therefore, up to now, various AI models, including expert system, machine learning, and deep learning, have been widely used for NPM. And these papers use AI-based linear programming workflow, including building linear model, covering, prospecting data, constructing models, generating linear rotational maps. Linear diffusion model meaning represents the metal heat, fluid source, hydrogen transport, and metal deposition. Prospecting big data, including geological, geochemical, geophysics, and remote sensing data. AI models were used for feature extraction and fusion for shadow machine learning, but for deep learning related to the raw data. In addition, we usually apply the set series and RC curve to evaluate the NPM model's performance, and this is the AI-based NPM workflow. After all, random forest is the most common machine learning operation for NPM due to its ensemble learning approach and minimal parameters tuning requirements. It has the following advantage: feature important assessment or evidence layers, robust handling of recent values, and can be deal with different types of input. Also can be have generation of reliable maps. Also, whereas deep learning has been used for NPM, including the stack autoencoder, deep leaf network, recurrent neural network, convolutional neural network, generative adversarial network, and graph neural network. Now, convolutional neural network (CNN) is a popular deep learning algorithm for NPM. It has 3 key hidden layers. If the hidden layers more than 2 layers, and called this machine learning can be the deep learning. And CNN has the 3 key hidden layers, including the convolution layers, pooling layers, and foreign connection layers. Convolutional layers can be used for prospective information extraction, and pooling layers can be used for key prospective information capture. Foreign collection layers can be used for anomaly detection and predictions. Finally, I would like to talk about the data logic during NPM. As we know, owing to the complexity of mineralization process, the variety of mineralization events, the diversity of mineralization features, and the black box nature of AI. AI-based NPM face the following 5 key challenges, including inadequate data representation, insufficient training samples, poor robustness, weak generalization ability, and insufficient interoperability. The first challenge is the inadequate representation of prospective data and spatial coupling relationship. In terms of the data formats, AI can be classified into pixel-based, image-based, and graph-based models. Pixel-based models such as random forest typically ignore the spatial relationships of mineral deposits and the laborious areas. Image-based methods such as CNN have the fixed size and shape of the input image, which may hinder the full integration of the spatial anisotrope of mineralization. How to solve these challenges? We use the graph neural network. The graph composed of the nodes and edges can capture the complex nonlinear spatial relationship between loaders and then can characteristics in regular geological units. Therefore, we use the graph to denote the spatial data, such as the geological, geochemical, geophysics, and then data, and don't use the we input the image, not the pixel, not the image, and we put the data as the graph composed of the loaders and elements. The second challenge is the insufficient training samples. As we know, generalization is a real event. Therefore, if AI model can, if we want to train AI model, we need to amount of training samples. That generalization is a real event. So therefore, we lack of training samples. And sometimes we really use the data augmentation, such as sleeping, rotation, and flipping methods to increase the training sample from 10 samples to 100 and 1,000 samples, training samples. In fact, those methods may be offer geological interpretation and therefore not be used for exploration. Therefore, we developed two new geologically considered data augmentation methods to depend training datasets. First is the random drop-based data augmentation methods that can depending the number of training samples by adding random zero noise. Another is to use the GAN. GAN can capture the complex geological features from raw data using adversarial training and generative synthetic samples. And those two methods can take the geological meaning and also can generate the diagnosis of the training samples. You can stimulate different style of mineralization. Therefore, two methods are suitable for training the NPM. The second solution is to employ semi-supervised and self-supervised learning methods. Those focus more on leverage models, architectures, and the mechanism to effect the underlying features precisions of data. And those two methods is suitable for study well, and there is lack of training samples. And the third solution is applied reinforcement learning, and it's a new learning methods and new application applied. Reinforcement learning enables the models to not only leverage the mineralization information from the labeled samples, but also to explore the potential information from the unlabeled samples, and therefore it's very useful that there are few application of reinforcement learning in NPM. I think we need to further develop methods NPM based on the reinforcement learning methods. And the second is for here I just want to refer to noisy, and noisy can noisy typically result from the unpresentative samples, missing data, sampling errors, interference errors, and reduction information. And those two features the weights and the value uncertainty of layer due to the noise. You can find the different method can be have the different weights due to the noise. So the models, the robustness can be affected in the robustness of the AI models. So we need to deal with the noise. We propose the Monte Carlo simulation and risk written to deal with the poor robustness. Here, Monte Carlo simulation quantify the impact of uncertainty on models' robustness, and we can get more realization using the simulation and molecular simulation. And we then calculate the mean and variance, geological risk and return. Here, risk and return analysis is carried out to guide visualization. Sometimes we should select area in the high region, or here the probability for the formation of realization, and the low risk, here geological uncertainty or bias. So we should select the high region, high probability, and the low risk or low bias area for winner visualization. And the fourth challenge is weak generalization ability. Error generalization ability refers to the ability of a model to perform well on C data. Fortunately, its ability to make good prediction performance on data loss involved in the training. For example, here we training AI models for TM, and maybe the model is not still suitable for another study area. Therefore, the generalization ability is lack of generalization ability. Here, we propose to use the transfer learning that can be applied to the knowledge from the web data on one study area and transfer another study area, including the transfer the generalization rules and AI models architectures and AI models parameters, and from study area transfer another study area, and then improve the learning efficiency of the new task and improve the generalization ability of AI models. And the transfer learning should be used to improve the generalization ability. And the last challenge is in such the interoperability. Interoperability refers to the ability of models to provide clean reasoning process and decision basis, allow its prediction to be confident and verified. However, AI is a black box, and we need to ask, why does AI make this decision? How does AI achieve this? AI without be tested. Therefore, there are three questions we usually ask. So, in order to improve the interoperability, we need to come from the input data model design and output. Therefore, I will introduce from the data reset and the model of design and output quantum, improve the interoperability slow at launching into the models. First, this I shows the how to improve the data interoperability. Here, including the start dataset based on your system. What data, what type of data should be collected? We need to based on inner system. You need to study the how and where the innovation form, and how about the source, transport, and position, and according to the study with the system, and then we can collect the data. Also, we need to use the feature intelligence technique for data cleaning, and especially deal with the noise reduction information. And three, is providing the model with the integration training samples. And I have been and discussed how to generate the training samples. And this I consider for the data interpretation. The second most important, I think, is the node interoperability. Here refers to adding prior knowledge into the model design process. Here, including the construction of the hidden layer. I mentioned before, implementing consists of the input layer, hidden layers, and the output layer. Here, we add the biology into the deep learning. So we construct a new kernels based on the linear system, and then based on the geology, we add a term loss truncation, which aim to guide the AI model training working with the domain knowledge, also working with the things themselves, and this for the model interoperability. The last, the result interoperability is achieved using the closed-hook interpretation techniques to deliver the underlying logic and reasoning behind model decisions, especially layer-wise visualization to help in understand the model operation with output layer by layer and see the output, what output. Also, it uses the feature of attribution algorithm to quantify the contribution of each input vectors. Based on above activities, we also propose a new generalization of AI models when it has major three advantages. First, it allows for the integration of required geological and expert quantities into AI models at a well-balanced stage of the modeling process, offering certain degree of transparency about the information transfer process while also improve analysis and evaluation of improved features. Last and second most important can detect new information, enhance linear regression targets, and promoting the advancement of linear technology. And I think this the new generation of AI models for MTM. Also, we also further propose the concept of simple AI models to MTM. It is including two important improvements. First, it confirms more transparent and explainable AI models to MTM by embedding domain knowledge throughout the AI-driven MTM, from input data to mode design and mode output. The second, providing strong knowledge and conceptual needs that guide the entire AI-driven MTM model training process. Thereby, the model can improve models' interpretability and performance. In addition, we also propose two large models for MTM. The first model is the not-constrained self-supervised graph transformer models. Here, we use the graph to deal with the inadequate data representation, and we apply the self-supervised method to deal with the inception between samples. Also, we use the pre-training and fine-tuning to deal with the weak generalization ability. Also, we use the geologically constant models to increase the inception interoperability. Also, we use the transform. With new models, the AI new models can capture the long-range dependency. And this ladder displays, this ladder shows the larger methods called geological constant graph reinforcement learning models. Here, we use the graph to deal with the inadequate data representation, and use reinforcement learning to deal with insertion training samples, and also we use the geological constant model to improve the interoperability of AI model function. And these two pictures use the final rotational map obtained by those two new models to be found more low-minority bodies are located in the red area means high probability, meaning new models have strong performance for predicting the minority bodies. Also, we use both the success rate cars and LC cars to evaluate those two models we find those tools to have a good performance. In addition, we propose a large data multi-user framework that covers AI with inner system, helping the system deduce the metadata and deploy the source and fluid transport and method fishing for enhance the MPM occurrence and reliability. And this the architectures of the models. Also, the big shows the architecture of data multi-user models. This model can guide the sections and proceedings of geoscientific data for mineral integration. For the data section, new source geoscientific data are chosen based on mineral system process. For indicator detections, source, transport, deposition branch is designed to detect or control indicators. For model fusion, the geological models derived from the mineral system is added into the fusion branch with aim to enhance both the interoperability and predictive performance of the AI models. And this slide shows the predicted spatial distribution of all controlling factors, including enzyme intrusions, force, geochemical they denote the source, transport, and position process in mineral system respectively. This slide shows the final prediction map, and this curves compared with the pure data models and the geometrically considered models. We can find if we add the geological into the AI models, it can improve the performance and also it can be improve the observability. Also, we have developed the ArcMap. This is the engine-based software for MPM. This software has added the several channel machine learning and advanced learning I discussed. There are so many advanced methods can use for MPM. So if you want to use this method, you can electronically find this open source and currently in visual research. If you want to look, you can download the paper. Also, and then there's our conclusions. First, AI can effective analyze and integrate for fetching big data, building nonlinear matching relationship between prospective data analyzation probability. That intelligent NPM with self-changes, first including the inadequate representation of geological prospective data and the spatial coupling ability. In substantive examples, for most robustness, limited generalization quantity, and lack of interoperability. Based on those strategies, I propose 7 AI models for MPM to better to address the above-mentioned issues, including the adjoint constraint self-supervised graph transform model, or geologically constrained graph reinforcement learning, and finally, a large data knowledge build framework that covers AI with inner system. So what details you can further read the reference. Thanks for your attention. If you have any questions, you can email to me and we can welcome your questions.
Do I have to stand voting or I can just speak from here? So we have allocated some time for question and answer session. So for those who are online, if you have any specific question, you can either type it or you can just raise your hand and unmute and then ask a question. And those who are in the classroom, feel free to raise your hand and also ask any question that you may have. And it doesn't have to be very advanced questions. It will be as fundamental as how do you get started with one of these types of work, or what sort of data do you have to have for you to be able to do this type of work. And if you are an honors or an MSc or PhD student, you can also ask any question relating to your project that involves modeling. So feel free to use the opportunity for engagement?
First, you want to know about the data. Yes, the combination. Yes, I think it's most important. The governing in and governing out. Therefore, what type of data should be collected? I think first we need to study the mineral system, how, where, and when the mineral deposit formation, and we need to describe the source, including the metal, plate, and the fluid source, and then how the fluid transport to the deposition zones. So we have a better understanding information of mineral deposit, and then which data can denote the source, which data can be used as an indicator for the transport, and what's the data can be used for reading the deposition zone. Yes, and I think this is the base. We need to how and we can collect the data. I think that's very important.
Is there any particular software that you use for this?
No software just can be used to processing your data. But which data should we have input the AI model based on your maybe your experience, and maybe you have connect what the data. So here we need to domain knowledge.
It's again. You showed a little bit of GANs, generative adversarial networks. What limitations do you think there are for generating geological data, or do you think there are no limitations?
Yes. So I think there are many challenges for this mineral condition, especially for the geological ability. Because different study area maybe have the different type of mineral deposit, and maybe the source, transport, and location are different. So when you build an model for one study area, maybe the architecture and the parameters and also the input variables maybe suitable. This study a large study maybe is difficult. So I think this is a very important, and we maybe face the most challenges, because we spend a lot of time to build a model, but we just use only once. I change other design. Oh no, the model output of the model. Oh no, so I think we use the transfer maybe help transfer what? Maybe I think it's three key components, three key difference. Because then we can transfer formidability to them for hydrothermal mineral system. Maybe the source, the transport and fluid are similar, and this will first. And then we can transfer the structure of models, also transfer the parameters of models. For them, how many hidden layers from them in this study, and only 3 layers, and possible maybe use the cylinder. So transfer 3 factors. One is the terminology, and other is the AI structures, and also AI parameters. Simply. Thank you.
Okay, yes. I was delighted you pointed out the issue of poor quality training data, because poor quality geological data has been a problem in my entire 5-year career. So one of the things I could see this could help is to train a new generation not to produce bad data, because it just never gets any better. And unfortunately, your solution requires a certain quality of data. Do you see that as something you could used by looking at old data and pointing out to mining companies that they have wasted literally millions of dollars of work, doing lots of work, but what they ended up at the end isn't really very useful.
Yes, 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 I agree with you. First, we need to use all the data, the history of the mining and in the source of the data. But there are a problem because the spatial solution of given the data and maybe and the data errors different and if the data generated from different ages, for example, 10 years or 10 years of data and now maybe the errors are different. So how to fuse the different source of data? How to use the data generated from different time? I think it is very important. If the training data are wrong, maybe the AI models or tools is wrong. So first we need to keep the inputs for AI models are correct. But how to pick the big correct and how to pick the data input the AI model are useful. If you input the garbage, maybe you get the garbage out. I think it's very important. So we need dominance, we need experts, big theories, we need experts knowledge to define, to refine our data. Yes, this is my thinking. So
Thank you.
There's a question from someone online. The question is, how does AI handle greenfield exploration data where you have very limited data?
Yeah.
So how do you do NPM there?
For the limited data has two means. First, if you in your scenario, just only your geochemical data, and we have the geophysics data or geological data. This one is the analytical tree samples. Yes, and in our scenario, the just only 7 million deposit and could load to generate the tree samples. Yes, so that only for the first case, if the limited data, for example, you just have the geochemical data and no geophysical data to content. I think they're going to be used AI model. You can simply use the chain machine learning just as the random forest, and you can tender sampling sampling correlation because there are limited variables. Yes, and limited data means there are limited variables, just 6 or 10. But if you have many data, maybe have many variables. So if you have limited variables, you can use the chain machine. But if you have many variables, you can use deep learning to deal with or to mine the hidden correlations where different amount of variables. But if you have big data, you just can use the chain machine, such as the random forest or the postmodel machine. It's very useful to deal with the limited variables. A last case study, last case is if you limited the low meter deposit, meaning there is insufficient for the training samples. You need to use the augmentation to increase the training sample. For example, you can increase one sample to 1,000 to 10,000 training samples. Other is use you can use the self-supervised training learning, or you can use the semi-supervised learning. Also, you can use the first learning because they can import the leadership between samples. You can combine the labeled data also can combine the unlabeled data. and the input limited number of these samples. So it's nothing.
Okay, so to build up from that, what if you have data with different resolutions? So for an example, I have geophysics magnetic data that was collected at a scale of 1:50,000.
Yeah.
And I have geochemical data that was collected at a scale of 1:10,000. How do you deal with that?
Yes. I think it's very common in linear integration. We usually face different spatial solution. Yes, how to deal with this? I think we need use the inverse intent methods to resample to different spatial solution data into the same spatial data. I think maybe this is the best method. You can use the inverse intent methods to integrate the course spatial solution data into the file. Yes.
Online, those are the Google ones.
Yes.
Please start press next to begin.
Can we utilize AI and machine learning for resource estimation?
Great.
How can you utilize AI for resource estimation?
For research,
For resource estimation, typically we use trading or inverse distance weighting. Can you use AI for resource estimation?
Yes. AI can use it to look for the two frameworks, and many people use the motion to estimate the value of any location. Yeah. Because, for example, you can use the random forest or support worker machine to like the inverse intent method to evaluate any value, any location. Yes. Because you need to build the relationship between the input and input variables and output. You can build the relationship the data location, and I know the value and I know the input variables, and we can build the quotation, and then we can use the quotation to repeat anywhere the values.
So maybe to follow up on what he has mentioned, given that the data that you collect if you work in a mine are point data in a form of boreholes, but your output is going to be graded data in a form of block models. How do you work that out?
I think the 2D will say the 3D is different from 2D. It's just if you explain the 3D to 2D, the same procedure. More than less used in the 2D, also can use the 3D.
But I'm talking about change of support. You are moving from points to a block.
Yes, when you put the block. Yes, that's 3D. But when you represent the data, they just show the paper. Yes, they are similar with the 2D. So,
Right.
Yes.
Is there a hand? Oh, yes.
I wanted to ask if the data that we're collecting is able to be disseminated to the public, to civil projects and things like that, or that's more so something that scientific communicators would need instead of specifically geoscientists.
Leo, you were close to her. Can you repeat it?
Yes, so
No, he's going to repeat.
I think what we're trying to say is all the data that's been collected, all this information that's been gleaned, is this able to be shared more effectively by that for non-scientific communicators?
anything is
The information that's collected and then information you interpret.
Yeah.
Is there a better way to disseminate to people in the industry as well, society, everybody, or does that fall on geoscience, geologists alone?
I think the method can be used any programs. I can use them for video regulation. Also, you need to use the environment study. Also, you can use them to identify technologies you need to innovation. Also, if you focus on your science program, you can choose one word method to deal with your work. And I think the method are solid. You can use them to another subject. Yes. Question? Okay.
Anyone with that? I'll just check for one more round of questions to see if there is
There's
anything.
one question, is this going to be shared, or at least the references on the last page? You
Please repeat that.
Will the whole presentation be shared?
So this will be on YouTube, meaning that you can watch it anytime if you want to replay it. So the whole thing is going to be shared on YouTube on the Geosciences channel.
There's one last question I had about creating the additional samples that you said, because the sample spacing is so wide, you're able to create those. If we don't know what the real association is between adjacent samples because we haven't done enough research, haven't you got a chance of producing hallucinatory samples that could affect your model?
Yes, because the limited training samples, we have no ways, no other better ways. So I must immediately choose to simulation the training samples. Otherwise, if there are so many training samples, I think we don't need to do. That's for mineral deposits. As you know, it is real events go into in the software in the number of mineral deposits. But like the dogs, the caves are so many here. So if you could capture the mineral deposits features, of course, in the world, the no same deposits. Yes, maybe some features are different. Even so, in the same area and for the same type of mineral deposit and some different in the deposit. So we have no ways to no good ways to get these that to get the large number of training samples. But AI, if you want to train or groups performance of the AI models, you need include many training samples. So we need to generate training samples through simulations. Also, there's dangerous because maybe your simulation results is not devoted to the mineralization, maybe it just loss. So how to keep the correct training samples? I think maybe you can classify into your training sample into different groups and include their models, and then look each output are similar with others. If the output are similar, okay, maybe the training sample. Otherwise, one output is good, another is bad. Maybe our relation the training sample are wrong. So,
is there any metric that you can use to assess the quality of your simulated or generated training data?
Yes. In 2002, maybe in the middle in some country, and as we know, the low energy cost can be regarded as the positive example. But also we need the negative example. How to generate the negative example? We can random select point. Yeah, so we generated 1,000 negative examples through random select point, and then we group those 1,000 collected samples into 10 groups, and then input the positive criticism and negative criticism for the random points, and then we can calculate the 10 outputs. Yes, and then we can calculate the mean and variance of the 10 outputs, and the mean relative the average of output, but the variance relative to the uncertainty and unbiased due to the selection of that business. Yes, I think this is a better way to evaluate the impact of the simulated training samples and the AI performance. You can calculate different training samples and calculate the mean and variance.
I have another question here before we close, which comes from Kennedy, and it says for a beginner, somebody who's starting out, how do you start training your data? Is there a specific workflow that one can use as a beginner?
Yeah, you mean how to train on AI models? Yes. Yes.
Yeah. So how do you begin? Is there
Yes.
is there a standard workflow that you must follow?
I think there are 3 steps. First, you need to focus on your scientific problem, which is calculating or predicting. Yes, different tasks. You can choose different methods. Yes, maybe some tasks just calculation for example different work types, and after we calculate the probability high or low, because for example for the middle probability and the high probability denoted the high chance for fundamental hypothesis. Yes, so first you need to focus on your scientific problem, which is the calculation or prediction, and then you need to choose the methods. They depend on the data we said. If the data are very complex, for example, you have so many variables, you need to choose differently. But if your data has several variables, you can choose very simple model like the random forest or the photo machine. Then I think the subset you need to apply the feature engineering for the data clean. As I say, coming in and coming out, you need to keep the inputs of the AI are useful and quick. Otherwise, maybe the whole thing is wrong. So I think as I said,
Are there any free online courses that somebody can take to learn this?
Online course, no, because as well, I just focus on research. And
No, I'm saying from anywhere. Is there a platform where you have free courses?
yes, my 2 lessons will be available online in the International Institute of Science. So
Right.
I will send the link to you. And the first is a lot is big data and AI. I base the token data to singing. Yes, and 2 pages will be online. So if someone are interested, you can download from the ING site.
All right. So
Yeah.
please share the link and then we can display
Yeah,
it to
yeah,
all
yeah.
participants. Is there any other question from anyone?
Yeah.
So if there are no questions, we just want to say thank you so much for making time.
The picture?
And yes, you can take the picture. And what he has asked is that before he leaves, for those who don't mind, who would like to get a group photo. But firstly, I just want to thank a few people who have organized this talk. The first one is Professor John Coranza from University of Free State. He's the one who introduced NPM to South Africa a couple of years ago. And secondly, of course, our guest or our speaker, make time to actually come and spend time with us. And he's quite open to also share knowledge, meaning that you can email him anytime and he should be able to assist you in different types of projects. And lastly, he's also a mentor for the Society of Economic Geologists. So if you are interested also in mentorship, feel free to reach out. And he's happy to also connect you with other people. So with this, I just want to say thank you, the School of Geosciences. Now, I think let's take a group photo. Your name is still there, so it should be okay.
Yes, okay.
For those who are online,